In computer graphics, when creating the three-dimensional scenes, we want them to look as realistic as possible. We can use ray tracing to accomplish this by adding shadows, highlights, and reflections. Ray tracing simulates the path that light takes from an object to the eye and traces it to determine what color it will be when it hits the eye. This process is a lot more complicated than it seems. First, you have to determine which direction a ray of light will take when it hits its source. There are literally millions of directions that light can travel. For example, consider a ray of light from your bathroom light bulb. This particular ray of light hits your chin, some of it is absorbed, and the rest of the light is reflected in the color of your skin. The reflected ray is then reflected again by the mirror in your bathroom. This ray hits your retina, which is useful, otherwise you would not be able to see yourself shaving. In the same way, a ray of light in the virtual camera gives the color of one pixel. In ray tracing, the main problem is to find the nearest intersection of the ray with an object. Because there are often millions of objects in a scene, simply checking the ray against each object is very inefficient. Often, a ray tracing algorithm cuts down on the intersection checks by using a spatial index structure. Using such a structure, we can check if a ray is in the vicinity of the object before we check for an intersection. Of all the rays of light that come from the light sources, a lot of rays do not end up on our virtual camera. We only want to know about the light on our virtual camera. For this reason, we follow the rays of light backwards. This means we start at the virtual camera and trace, or follow backwards, the ray that determines the color of the pixel we want to know about. If we encounter the point where the light is coming from, we want to know the color at that point. To compute this color, we need to know what the incoming light at that point was. The incoming light consists of the light that falls at that point, so we recursively trace those rays. Generally, the process of ray tracing can be compressed into 4 steps. First, we generate rays originating from the camera. We then follow the ray to a spatial index structure, such as a grid. For each area the ray passes through, we calculate if the ray intersects with an object in that area. If there are no intersections, then we continue traversing the next area of the grid. If the ray does hit something, then we calculate the color of that point. This is also known as the shading computation. The shading computation may require that we trace more rays. This makes ray tracing a global illumination rendering method, as these rays can come from both light sources and other surfaces. Computer graphics are using increasingly complex scene and advanced visual effects, and are nearing the boundary where ray tracing becomes more efficient. This boundary has already been crossed by state-of-the-art applications.